Now we're going to introduce summation notation. So let's say you have a bunch of numbers, so 1 number, 2 number, 3 number, 4 number, 5 number, 6 number, say 7 number. So we have 7 different numbers and we want to add them all up. And the numbers I can think of as forming part of a sequence, which is why I use this notation. So you can see that's very tedious to write out something plus something plus something a bunch of times. So what we have is we have the shorthand notation. What we do is we put this symbol here, and then we index these, and the index, so I called all these objects A objects, so you have object A1, A2, A3, onto A7. So the way we use shorthand notation for this is, since we're calling all these A objects, then we put object A here, and then we put any other symbol we want here. So for the moment, I'll use the symbol, say, N, and then we can say we're going to do summation N equals 1 to, say, 7 over the ANs. So I'll explain this notation, and I'll tell you how to read this symbol here. So when you see this whole thing, this whole thing in words is the sum from N equals 1 to 7 of AN. That's how you would say this in words. This is the summation. The sum from N goes to 1 to 7 of A sub N. So a couple of terms here. So again, just as with sequences, this is the index, N is the index, and you have to specify the range. The index needs a range. So am I summing over the first 7 objects? And so you have to have, basically you have your range. So this is the lower end of the range. This is the lower bound of the range, and this is the upper bound. And this is reminiscent of integral notation. And, well, that's pretty much it. So this is called summation notation, and it's also called sigma notation, and that's because this symbol here is sigma, which is a letter in the Greek alphabet. So that's Greek alphabet. It's actually capital sigma. It's capital sigma. So like in English, we have capital, just using ordinary print, capital S and little s, they look the same, but in Greek you have capital sigma looks like this, and little sigma looks like that. But anyways, so this is called summation notation, but you can also refer to it as sigma notation, since we use the Greek letter capital sigma. And it's just good for you to be comfortable using this notation. So we'll do just some examples. So the first example, let's say let's do the summation. N goes from 1 to 6, and now what are we going to sum over? Let's sum over these objects, say 2n minus 1. Okay? So what does this mean? This is a short notation for doing the following thing. So I'm summing over, as n ranges from 1 to 6, things in the parentheses. So I have to do like 2 times 1 minus 1 plus 2 times 2 minus 1. Sorry, miswrote that. Plus 2 times 2 minus 1 plus, now it's 2 times 3 minus 1 plus 2 times 4 minus 1 plus 2 times 5 minus 1 plus 2 times 6 minus 1. Okay, so the right-hand side is, that's a lot to write out, and so the shorthand notation is very, 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 very convenient. And of course, we can actually sum this up. So that's 1 plus 3 plus 5 plus 7 plus 9 plus 11, which is equal to 12 times 36. So that's an example of what this notation is, and it'll be convenient to understand properties of how these things work. And so let's briefly review of the summation notation. Because in practice you'll have large sums that you want to do, and you're going to rewrite them using the shorthand notation, and so it's convenient to be able to just do the calculations using the shorthand notation. It's impractical to expand everything out. So here are the main properties. So summation, now I'll use, so k goes from 1 to n of some constant. So c is just some constant. So this is equal to c times n. And that's the first property. And this should be kind of obvious, because what you're doing, you're summing over the objects k now when k ranges from 1 to n, but each of the objects, I always spit out c. So you have to spit out a c, that's for when k is equal to 1, plus another c for when k is equal to 2, plus another c for when k is equal to 3, plus another c, and you just keep going. And then you do n, so you have in total n copies of c, and that of course is just c times n. So that's the first property. So if you have a constant. Second thing is that it behaves well with respect to addition and subtraction, but you have to have the same ending points. So let's say k starts at m and ends at n, and m and n are just dummy symbols. It doesn't mean that n is the next thing after m. But say you have some a k plus or minus bk. So what is this equal to? Well, you can just split up the sum. This is just essentially the commutative property. You can just do the first sum, and you can add to that the second sum. So they distribute, finite summations distribute well over addition. And again, this is just the commutative property. This property too is essentially just the fact that addition is commutative. So for example, if you wanted to do a summation, just as an example, say k goes from 1 to 3 of a k plus bk, then by definition that means you're going to do a1 plus b1 plus a2 plus b2 plus a3 plus b3. So that's for k is equals 1, that's for k equals 2, k equals 3. And of course this is all addition, so you can just rearrange the order. So that's like a1 plus a2 plus a3 plus b1 plus b2 plus b3. And then you can go back to the shorthand notation. So that's summation k equals 1 to 3 over the a's plus summation k goes from 1 to 3 over the b's. So this is essentially just the commutative property. The fact that we can rearrange addition. Addition is commutative, so we can just swap the order of things like that. And similarly with subtraction. The third property is that you can pull constants out. So you have a summation, say k goes from m to n of c times some ak objects. You can just pull out the c from the summation. So that's another property. And so this is just the distributive property. Sorry, that's an example. We can ignore that. So this is just the distributive property. This is the distributive property, which you are all familiar with. So just to make this clear, say summation k goes from 1 to 3 of 2 times ak. So again, that means that you're going to be 2 times a1 plus 2 times a2 plus 2 times a3, but by the distributive property you can just pull out that 2, a1 plus a2 plus a3, and then go back to the shorthand notation. So that's summation k goes from 1 to 3 over the a's. So it's just the distributive property. And fourth property just says that you can split up a sum into smaller components. So if I wanted to do a summation, say k goes from m say k goes from m to, say, n of some objects, ak objects, and then I can do a summation. K goes from, well, after the, so here, like this is, okay, n plus 1, and then we'll go up to, say, p of ak. That's the same thing as summing over from m up to p over the ak's. And again, this is obvious, because here, so, because first you start here, and then you stop here, and then you start again, and then you stop here. And so if, after you stop the first time, if you restart one higher than it, then it's the same as just putting everything together. I'll get rid of that. So again, these properties are supposed to be obvious. It's just the notation makes it look kind of weird. Let me get rid of these red marks. So these properties are supposed to be obvious. So for example, if you do summation, k goes from 1 to 2 of ak, plus the summation k goes from 3 to 5 of ak. Well, what's that? Well, the first summation is you do a1 plus a2. That's coming from this first summation. And then you're doing plus, that's this plus here. Then you have to do this summation, and that says we're going to do a3 plus a4 plus a5. So all together, that's shorthand notation, summing from 1 to 5 over the a's. So these are the properties of summations.